this presentation. Okay, can I start?
Yeah, please start.
Okay. My presentation today is the discrete adjoint-based optimization methodology and applied research for laminar flow weighing. As we all know, drag reduction is one of the eternal goals pursued by aircraft design. There are several ways for drag reduction, such as using composite material, a new layout, and the laminar flow control technique. The laminar flow control technique aims to lower the skin friction drag. For the typical commercial aircraft, the friction drag can be up to almost 50% of the total drag. And the laminar skin friction drag of the laminar flow is much lower than that of the turbulent flow. As investigated, for the typical commercial aircraft, if the laminar flow control technique be applied on the main wing, nacelle, and the fins, the total drag reduction can be up to 60%. It is a fantastic improvement for the aircraft design. Usually for the laminar flow control, the natural laminar flow and the hybrid laminar flow are two main approaches for delaying the laminar to turbulent transition. And there are also 2 points I have been working in recent years. Here I showed laminar flow control development history from 1930. It includes both the natural laminar flow and the hybrid laminar flow. The results include the flight tests and wind tunnel tests. Note that for the Honda Jet and the Piaggio aircraft, the natural laminar flow is applied on the main lift surface, the wing. While for the large CV aircraft, the laminar flow control is mainly applied on the components of the large aircraft, like the winglet, the nacelles, and the fins. So for the main lift surface, such as the wings, they are mainly the flight tests and wind tunnel tests for the research purpose. So I think what blocks the development of laminar flow technique on the large CV wings. So let's first focus on the physical characters of the large CV aircraft wing. The wing owns the moderate or large sweep angle and a high real nose number. These two characteristics makes the transition complex, including both the time scooting waves and the cross flow vortices. When the real nose number is very high and for the large sweep angle, the natural laminar flow fails, and we need the hybrid laminar flow. This also shows that for the high real nose number and the large sweep angle, it is more difficult to delay the transition. And for the time scooting and the cross flow, the pressure gradients are opposite effect, such as for the favorable pressure gradients, it can amplify the cross flow, but suppresses the time scooting instability. And also for the transonic flow, and in the design process, we need to balance the shockwave induced drag, skin friction drag, and the pressure drag. Those characteristics and challenges the laminar flow control applied in the large CV aircraft wings. I summarized the 2 topics for the future laminar flow wing design. The first one is before the design, we need to develop a robust transition method suitable for the high real nose number and the large sweep angle. as we may apply the hybrid laminar flow, we also need to capture the effect of the boundary layer section. The other one is we know that the traditional laminar flow vein optimization method is inefficient and faces the dimensionality curse and making it difficult to meet the development trend of the for aircraft design with large-scale design variables. For the first topic, we need to build a robust transition method. As we all know, the Yayun method is widely used in the industry application. So in today's topic, I also use the Adjoint-based method. In this part, I implementing the vendor tunnel or the flight tests to validate our code. And meanwhile, those valuable experiment data were applied for the calibration of the transition prediction method. Here is several experiment tests are carried out in China recent years. And these 4 experimental tests that I have participated in. This one is transonic wind tunnel test. For this configuration, it has a large sweep angle. It is 35 degrees, and this wind tunnel test is designed to study both the natural laminar flow and the hybrid laminar flow. This is a wind glue flat test. It corresponds to a moderate or high Reynolds number. And this is a flat test on the unmanned aerial vehicle. This is a real aircraft wind tunnel test. It is the COMAC 919. It is used to research the hybrid laminar flow control. Today, I will focus on these 2 experimental data. Here, let me first introduce our transition prediction framework briefly. The main idea is couple the resolver with the transition module. The transition module includes the laminar boundary layer code and the stability analysis. And the transition module would compute the transition locations. Then the updated transition locations are returned to the resolver by using intermittent function. These two systems iterate until both the transition locations and the rest state variables are both converged. For the stability code, here we use the linear stability theory. The linear stability theory code is to solve a generalized eigenvalue problem, and finally it will give the amplification factor for both the time switching and cross flow. And then it needs a critical n factor to determine the final transition prediction points. The critical n factor here, we can see it is very important in determining the transition locations. And the value is dependent on the environmental factors such as the noise, surface roughness, and turbulent intensity. And it is usually calibrated by the experimental tests, such as the flight tests and the wind tunnel tests. With those tests, the critical TS and the CF critical n factor can be plotted as a diagram. Here it is a diagram plotted by DIR, and we can use the diagram to check which critical n factor we should use in the study under similar condition. Then I focus on the wind tunnel test for the transonic speed. For this configuration, it has a large sweep angle with 35 degrees, and this test is implemented in the Aircraft Research Association wind tunnel, and it is low turbulent intensity. For this test, it is designed to research both the natural laminar flow and the hybrid laminar flow. So close to the leading edge, here it is a changeable panel. When it is for the natural laminar flow, it is a solid panel. When it is for the hybrid laminar flow control, here it is a porous panel. And the green range here is the test section. The test condition here, the Mach number is 0.7 and 0.78, and the real number is 6.5 million. The angle of attack ranges from a large negative value to a large positive value. The wide range of the angle attack makes sure that the transition mechanisms include both the time-scorching instability and the cross-flow instabilities. In the large negative angle attack, it corresponds to a large favorable pressure gradient. It means that the cross-flow instability dominates the transition. As the angle of attack increases, the favorable pressure gradient is reduced, and then the transition location moves downstream. As the angle attack increased and there exists the positive pressure gradient, then the time-scorching instability begins to dominate the transition. And as the angle of attack increased again, then the time-scorching instability are strong, and then the transition location moves upstream again. And the infrared images shows the change. And here for this finger, we shows the Mach number effect here. We can see that in the lower angle of the attack, because it is cross flow dominate the transition, and the high Mach number corresponds to the larger cross flow velocity. So the CF instability is stronger. Then finally, the Mach number of the 0.78 have the shorter laminar region. Well, for the largest angle of attack, as the high Mach number exerts stabilization for the time-scorching waves. So the high Mach number corresponds to a longer laminar region. Then I started to calibrate the critical N factor. For each case and maybe the size, we can get the amplification factor by using the CP by simulation of the experimental data. And we also have the experimental transitions, and then we would determine the critical N factor for the TS and CF instabilities. And we have more than 100 cases available. So finally, we could plot the critical N diagram here. And we can see the critical N factor is kind of scattered, and the scattered trend is similar with the results calibrated by DRR. And for the critical TS instabilities, the critical N, the average is close to 9, and for the cross flow, it is close to 7. And we use the calibrated N factor to simulate all of the cases. And finally, we found that 90% of the simulation results matches with the experimental data very well, and the transition location error is below 5%. We also carried out the hybrid laminar flow control, and the HLFC experiments are much more complicated. So we only carried out 2 cases, and the angle of attack is a large negative value. So it is cross flow induced transition, and we here mainly researched the section effect on controlling the cross flow instability. For each case, we carried out several mass flow rate, and as the mass flow rate increases, we can see that the transition location moves downward. And we also compare the experiment transition location with the simulation transition location, and the simulated results matches with the experimental data very well. And we also calibrated the hybrid laminar flow, the critical N factor here, and we found that the critical N factor of the hybrid laminar flow overlaps with the natural laminar flow, and this is very useful. We know that the hybrid laminar flow is much complicated and costs a lot. So if the under similar conditions, if the critical N of the natural laminar flow can be used for the simulation and analysis of the hybrid laminar flow, it would save a lot of efforts. We next experimented a flat test with moderate high real noise number, and for the wing glove configuration, it has a sweep angle at the leading edge with 5 degrees. So it for this test, it is the TS instability is dominated the transition, and we also calibrated the N factor. And for this factor, it is about 10. And usually, we previously showed the factor calibrated by the DIR. Sorry, there is some error on this finger. It is 9, not the 10. So usually, we show the previously critical N diagram by DIR. So usually for the flat test, the TS critical N is usually larger than 10. Here it is 9 because the flat altitude is only 7 kilometers. It considers the flat safety and make sure the real noise number as high possible as the red fingers shows the simulation and the experimental AR images. So for 9 critical N value, we can see the transition lag correspond to about 15%. While for the experiments, it is about 17%. So the simulation data matches well with the experimental data. The second case is similar with the first one. For the third case, and we have a much longer laminar region, and when it is up to the critical N factor of 9, the transition lag is about 45%, and for the experimental, it is about 47%. So the simulation results agrees very well with the flat test data. We also did the hybrid laminar flow to see the section effect on the Tom-Scooching instabilities. And we here for the this flat test in the section panel. We use the 4 chambers, and it corresponds to different volume flow rate, and that means the different section velocities. We can see from the simulation control, we can get the transition lab by simulation, and we can see that the transition lab by the simulation agrees well with the flat test data. Here we use the critical N factor calibrated by the NRF, and we got the good results. So in the future, we will also do more tests to see if the under the similar conditions, the hybrid laminar flow control, if the critical N factor of the natural laminar flow can be used for the hybrid laminar flow cases. With those 2 experiments, we verified our code and also calibrated the critical N factor, and the critical N factor can be used for other researchers in the future study their code by using the under the similar conditions. Of course, I verified our code by using the typical cases such as the airfoil infinite span swept wings. We show those 2 experiments implemented by us to verify the code when it is used for the large sweep angle of the high Reynolds number, which corresponds to the large civil aircraft. After the work on the transition prediction method, we move to the work for the optimization method. So nowadays, the adjoint-based method for the fully turbulent cases are widely used owing to its efficient solving problems with the large-scale variables. And for the laminar flow venue, finally, it would be facing the for aircraft optimization, which also a problem with large-scale design variable. So, and the adjoint-based approach for natural laminar flow veins design has some developments. However, most of the studies freezing the transition modeling, which would reduce the gradient accuracy and affect the final optimization. And there are some other studies which considers the transition models, but they are mainly developed for the 2-dimensional cases and uses the finding difference of the complex steps in developing the coupled adjoint code, and it reduced. It is inaccurate and inefficient. So I begin my work for the discrete adjoint-based method for laminar flow optimization. We first write those 2 problems as this. One is for the RANS solution with fixed transition location. The other is for transition prediction problem. And Q is the RANS state variable. It contains the density, velocity, pressure, and or temperature, and the turbulent model. And we use the Spallet amorous turbulent model here. So here it corresponds to the Spallet the SA turbulent model. And TR here is the transition locations and the transition length. And then with this equation, with these 2 equations, we can rewrite the coupled residuals and this. And then we can derive the derivatives of the residual with respect to the design variables. And then we can get the derivatives of the state variable with respect to the design variable. and we substitute this to the equations of the derivatives of the objective or constraints with respect to desirable variables, and finally we got these equations. And in the middle part, it is the coupled adjoint equations, which considers the laminar to turbulent transition. With the coupled adjoint solver, the previously built the Rance transition solver and the geometry parameterization and mesh deforming, as well as the gradient based optimizer, we can establish the adjoint-based laminar flowing optimization approach. Before we to solve the coupled adjoint solution, I need to explain something here. In the beginning, I used the exact linear stability theory method, and for the transition module part, as it involves the boundary layer integration, so it is theory processing. So for the whole transition module part, it only uses one processor. The linear stability theory is to solve the generalized eigenvalue problem. It will cost a considerable time, and more importantly, as we used the reverse automatic differentiation, so it will cost about more than 10 times than the original subroutine. So here, if we use the linear stability theory and the corresponding reverse automatic differentiation code, here it would make the whole coupled adjoint solution inefficient. So for the stability analysis, there are other methods like the simplified method. It is developed by Deraila, and it can capture the Tom-Scooching instabilities. And for the cross-view instabilities, we can use the C1 criterion. For the simplified method and the C1 criterion, it is just the algebraic operations. So the computations for both the analysis and the derivatives would be fast and save considerable time. We also compared those two methods, and the accuracy is close. For the Rance to transition part, only the linear stability theory is substituted to the simplified method and the C1 criterion. Then we back to the coupled adjoint equation solution. It involves 6 partial matrices we first need to compute. There are 2 main parts. One is related to the Rance solver, and this is related to the transition module. The first one is the partial Rance residual with respect to the Rance state variable. This part is kept unchanged compared with the fully turbulent solver. The second one is the partial Rance residual with 2 partial transition state variable. This term involves 2 systems, and we use the chain rule and reverse differentiation to express this part. In the whole coupled adjoint solution, we use the Jacobi free function. So we do not need to calculate the Jacobi matrix. We only need to calculate. We only need to the transport of the matrix product the adjoint vector, and finally we only need to get a vector. And for this term, we start from the rest adjoint vector, and then for it is the rest residual to the intermediate function, and for this part we just need to run the automatic reverse differentiation code and update it. This part is easy to get. For then we go to this term. It is a partial intermediate function to partial rest little variable. And this part it involves the MPI zero and the parallel exchange. So the automatic reverse differentiation code would fail here. We need to combine the head derivation and the automatic AD code, automatic reverse differentiation code here. And for the third term, it is the partial transition residual to the partial rest little variable. This term is the most complicated one. We started from the transition adjoint vector, and this is related to the stability analysis part. And for the if we use the simplified method and the C1 criteria, here it is just the algebraic operation, and so we can just run the automatic reverse differentiation code here. And if it is linear stability theory, we need to compare the head derivation with the automatic reverse differentiation to avoid to call the solver several times, and it would save some time. And then here it is the boundary layer code, and it involves the nonlinear system. And we also need to compare the head derivation and the automatic AD code, and to avoid to call the nonlinear solving the nonlinear system repeatedly. Then we go to the slash CP with respect to the surface CP, and finally in the rest solver it is the CP to the rest state variable. And for the first term, it is easy because it is identity matrix. For the right hand, it is the objective function of the constraints with respect to the state variable. So for this term, when the objective function or constraint is related to the false coefficients, it keeps unchanged. But when they are related to the transition locations, it is a zero vector. For this term, when the objective function or constraint is related to the false coefficients, it is zero vector. But when they are transition related, it is a vector consisting of constant coefficients. For the Jacobi matrix, we used the Jacobi free function and chain rule and the reverse AD code, which would save the memory usage and accurate and efficient. Then we start to solve the coupled adjoint. There are two methods for the coupled equation solution. The first one is the coupled Krylov method. It solves the coupled adjoint equation together. The other one is the linear block Gauss-Seidel method. For this method, we move the off-diagonal terms to the right hand. Then it results in a lagged system. We iterate those two equations until a target tolerance is reached. Those two systems is converged to their respective tolerance before proceeding to the other. For this function, the coupled adjoint equation looks like a pair of single adjoint equations with argued right-hand side. Therefore, we can reuse the existing Rance adjoint solver. This is the main advantage of the linear block Gauss-Seidel method. And for the beginner, this method would be easy to develop. After the solution, it is time to verify the solution. For the forward AD code and the reverse AD code, there always exists this dot product test. This dot product test is carried out to make sure the AD code is consistent with the original subroutine. More importantly, we know that for the dot product test is a necessary condition for accurate gradients computation. More importantly, you know that for the coupled adjoint system, it is very complicated, so we cannot get the right accurate the right gradients at the first time. So when the gradients is wrong, we need to find where it is a problem. So the dot product test can be carried out on the suspicious subroutines, and this is very useful in the debugging code. Here we show the 3 modules dot product tests results. The right hand and the left hand matches with each other very well, at least 10 digits. Further, we compare our adjoint-based gradients with the finite difference results. For the finite difference method, we run several steps and choose the optimal results, which is close to the adjoint-based gradients. And the adjoint-based gradients matches with the finite difference with relative errors at least 10 minus 3, given the error inherent in the finite difference approximations. Before we continue to the optimization, we compare the efficiency between the CK method and the LBGS method. For the 3-dimensional cases, the IBGS method is dependent on the under-relaxation factor, and the CK method is much efficient than the LBGS method. For the 3-dimensional cases, it would save 84.4% time. So in the following optimization cases, I will always use the CK method. We first start to optimize a laminar airfoil. It corresponds to a Cessna cruise condition, and the transition is sensitive to the geometry close to the leading edge. So we put denser FID points here. We have implemented the boost the laminar flow airfoil optimization and also the fully turbulent optimization. Firstly, I focus on the laminar flow optimization. It is the black and the red line. For the optimized airfoil, the radiance of the airfoil is lowered and the maximum thickness is pushed out. Finally, it results in a pressure distribution presents firstly a platform and then a weak pressure gradients. This will suppresses the time switching instability and moves the transition location after. For the lower surface, the pressure recovery strength is lowered and the transition location is pushed out. And here we note that for the optimized airfoil, the N factor is exactly up to the critical N factor values at the transition point. So it indicates that the optimizer explores the full potential of the laminar flow airfoil. As a result, the total drag is reduced by 52.7%, and both the pressure drag and the friction drag is reduced. Well, for the fully turbulent optimization, the drag reduction is only 9.5%, and it is mainly the pressure drag reduction. There is even an increment of the friction drag. We also, for the fully turbulent optimized geometry, we simulate the laminar to turbulent transition. We can see compared with the initial case, the drag is reduced, but the drag reduction is much lower than the laminar optimization case. This emphasizes that in the process of the laminar flow optimization, we need to accurately predict the transition and its gradients. Here I show the major iterations and the final intermediate results. For the point 2, we can see that the optimizer find a short region presents the favorable pressure gradients, suppresses the TS instabilities and moves the transition location after. And here it fed the optimizer continues to fed a longer favorable pressure gradient and moves the transition after again. And finally, the optimizer fed a platform shape and then a weaker favorable pressure gradients to move the transition location up to 75%. And for the lower surface, the optimizer tried to lower the pressure recovery strength step by step, and finally put the transition location after. The comparison shows how the optimizer optimates the natural laminar flow airfoil. The optimization process corresponds to the transition suppression mechanisms, which also verify our framework in some extent. Then we optimize a multi-point cases. The condition corresponds to the Hunan jet. It concludes the cruising and the climb cases. For the point 2 and the point 4, they are used to reduce the sensitivity of the final optimized shape to perturbations in the flat conditions. For the point 4, it is included to limit the minimum pinching movement, which ensures that the trim drag penalty and the high altitude and high Mach number is not that worse. For the optimized results, we can see that the section peak of the pressure coefficient increases and the favorable pressure gradient is lowered, and which moves the pressure recovery downstream. This would delay the laminar separation point, which ensures the possibility of the transition delay. Meanwhile, for the point 4, the shock wave is reduced a lot. And finally, the drag reduction is reduced a lot. This successfully optimization for the multi-point demonstrates that our framework is can handle the practical design. For the fully turbulent optimization, the drag reduction is much lower than the laminar flow. And interesting, we can see for the fully optimized geometry, we have implemented the laminar to turbulent flow, and the drag of this is even larger than the initial case. This again emphasizes that the accurate transition prediction and the gradient computation are very significant. After the airfoil optimization, we go to the quasi three-dimensional optimization, which was an infinite span-wise swept wing. And the sweep angle is 25 degrees. For the optimized results, we can see close to the stagnation point, the peak volume is lowered. And we know that the cross-flow instability close to the leading edge is most strongest. So the peak volume is lowered, and it will result in obviously decreasement of the favorable pressure gradient, which would lower the cross-flow instability a lot. And then finally the camber of on the up surface is reduced, which results in a weak favorable pressure gradient. This would suppress the Thom-Scooching instability. And as the cross-flow instability is not that large in the middle region, so the favorable pressure gradient will not amplify the cross-flow instability a lot and trigger laminar to turbulent transition. For the lower surface, the favorable pressure gradient is lowered to reduce the cross-flow instability, and finally the transition location moves downstream. And finally, the drag is reduced by 43.34%. For the fully turbulent, it is only 10.44%. The coefficients results comparisons are similar with the two-dimensional cases. Here we also show the major iteration history and the intermediate results comparison. We can see for the point 1, it is the TS instability induced transition. So the optimized to try to find the favorable pressure gradient to suppresses the Thom-Scooching instability. Firstly, a shorter region and then a longer region. For the point 3, as the transition occurs in the favorable pressure region. So it is a cross-flow instability induced transition. Then finally, the optimizer find weaker favorable pressure gradient, which would suppress the Thom-Scooching instabilities, but not amplify the cross-flow lot. And the last one, the optimizer tries to lower the pressure drag. This comparison shows that how the optimizer balances the conflicting of the TS and CF instability separations, and also shows our framework can balance the both the pressure drag and the friction drag. Finally, we applied our framework on a more complicated case, a wing body case. It corresponds to the conditions correspond to a typical regional aircraft, like the Airbus 320 and the Boeing 737. For the laminar flow optimization, the drag is reduced by 10.48%. While for the fully turbulent, the drag reduction is only 6.17%. And for this figure, we can see that the shock wave is reduced in January, and the transition location moves downstream. For the upsurface in the inner region, we can see the laminar region is up to the 20%. While in the outer side, the transition location is almost 60%. As the Reynolds number decreases gradually from the wing root to the wing tip, this is the main reason that the transition locations varies along the span-wise direction. For the lower upsurface, the optimized the transition locations is moved out in general. Let me conclude my work. So firstly, I established the transition prediction tool. It is able to consider multiple transition mechanisms and the effect of the boundary layer section. And we verified our code with 2 experimental tests. Second, then based on our framework, I derived the coupled adjoint-based equations and use the Jacobi-free function, automatic differentiation, and chain rule method for improving the accuracy and the efficiency. Finally, the coupled adjoint method is applied for solving the equation. And we also verified our code by the dot product test and comparison with the finite difference. And finally, we applied our optimization framework to for the 2, Q3, and 3-dimensional configurations. And the successfully optimization shows that our framework can balance the skin free drag, pressure drag, shock wave induced drag. And in addition, our framework is also able to balance the conflicting in suppressing both the time switching and the cross flow instability. So based on the adjoint framework, in the future, I would do the layout optimization and the 4 aircraft, which includes the nacelle, fins, main wings. And then I also would apply the adjoint-based sensitivity analysis to explore the principle between the pressure distribution of the suction control with the laminar to turbulent transition. This figure is shows that I calculated the calculate derivatives of the N to the CP, and we can see that the summarize the favorable pressure gradients is beneficial for reducing the sensitivity region. So the similar research would be carried out in the future. The third one is For the large civil aircraft, we need to use the hybrid laminar flow control. So the optimization work will also be carried out. Finally, as we know, use the Yayun-based method, and we need to couple the rest over with the Yayun method, and it costs a lot. So, and know the transport equation is popular, and we will implement the more flat tests or internal tests to development the robust transport equations, and then do the adjoint work. Okay, that's all. Thanks for your attention.
So thanks, Yayun, for this very involving and very mathematical presentation. So if you have any question, you can ask now, or you could also like type it in chat. So I have I think I can start. So Yayun, for your 3D aerodynamic shape optimization, I saw the optimized wing still have shock waves. Is that the case?
Yeah.
So do you know why is that? Like, should the optimizer be able to remove the shock wave?
I think you know that for if we remove the shock wave, it maybe correspond to like the positive pressure gradient, and then it will cause the Thom-Scooching instability cause the transition. So I think the finally results is considering the balance between the shock wave induced drag and the fixed drag, and also so for the for these cases, and the Reynolds number is high, and also the sweep angle is 20. So I think the natural laminar flow can only get the laminar region such as this, and I cannot get more better, much better.
I see. I didn't know that basic zero was a balance between the shock wave and the transition. It's very, very interesting. Yeah.
Yeah. So let me see this. Mm-hmm. So so for this optimization, the airfoil optimization, you can see that for the fully turbulent, the blue there, and it is have the much lower pressure drag. So it is positive pressure gradient, and then the transition would be induced by the Thom-Scooching. So for the three-dimensional case, it is very completed. It needed to balance the friction drag and shock wave induced drag, and it also for the shape optimization, it also needed to balance the conflicting of the two surprises, both the Thom-Scooching instability and the cross flow instability, because you know the like the pressure, the favorable pressure gradient is harmful for the cross flow, but it can suppress the Thom-Scooching instability.
I see. Thanks. And any other question from the audience? Could you explain more that how did you capture the cross flow stability?
Sorry.
Evaluate more about how the cross flow stability is captured. Like what equation you use, what you.
Okay. So in the optimization, we need to faster the computation and the optimization. So I used the C1 criterion to compute the cross flow instability, and here it is just algebraic operation. So we get the cross flow based Reynolds number, and we have the criterion, and we will compare this, and then get the final transition induced by the cross flow instability. And but for the linear stability, and we will calculate the cross flow instability in different wavelengths, and then compare it with the critical CFN factor and get the transition locations.
I see. Yeah, thanks. Any question from the audience? I guess if there's no question, I will stop recording.